so I might as well introduce myself. I'm David Brydges, and I'm going to give a lecture on an infinitely large subject, because it's going to be an infinitely small part of an infinitely large subject. So I want to explain Higgs mechanism, referring to some papers that come as close as we have in mathematics to being able to show that this happens for continuum models. So that's what dictates the rather small list of references here. So it's fun to read the Nobel lectures by Englert and Higgs, who mention a large number of other people who played an important role in this. These were 213. I've read this one so far, and full of nice stuff. Then there's a paper by Balaban, Imbri, Chaffee. Unfortunately, I had a problem with the internet before I came in, so I don't know that I've got the exact year. I'm going to reference 1984 because I was on that first paper. And I remember that, so I can look it up in my own publications, even though it's infinitely long ago. But these guys continued and discussed three-dimensional continuum Higgs model. I'll tell you what these things mean, of course, as we go on. But that's this, in other words, is as far as we've really got in terms of proving that the Higgs mechanism exists, and it's for a three-dimensional field theory in the continuum. And I'll spend some time on the part that I was involved in, because that contains an isomorphism that I think you'll find interesting between what's called non-compact and compact formulations. I'll explain that too. Then there's a paper by Kennedy King, which draws a more full picture of the phase transition than is in here. I fear I won't have too much time to mention that, but it's a pretty nice paper actually, with a lot of other things in it as well. And then there's Erhard Seiler's book. It's lecture notes 1982, lecture notes in physics. So this is good for lattice gauge theory. Contains, for example, big discussion of how to do things like cluster expansions for lattice gauge theories.
With a lot of errors.
With a lot of errors, yes, yeah. But it's still a pretty nice book. Yeah. I recommend that. So now to actually get started, I'd like to consider a finite subset of a unit lattice, ZD, and we will have a thing called the Higgs field, which is a function on this set lambda into complex numbers. Let's draw a picture. A two-dimensional picture. what I want to do is discuss dimensions bigger than or equal to 2. So here's a two-dimensional picture. And so phi is an assignment to each point in here of a complex number. So I'll sometimes write phi is in complex numbers to the power of lambda, just meaning functions complex from lambda to complex numbers. So alternatively, you can think of it as a big vector whose components are indexed by lambda. And then we also need a Yang-Mills field, which will be abelian in this case. A, which is a map from edges into the reals. So if we have a pair of points here, there's an edge joining nearest neighbors. And sometimes I'll use the language of differential forms. These are really nice and easy to understand because discrete differential forms. A function is also sometimes called a zero form. The A that lives on here, so A is a map from edges into the reals, has the property that AXY is equal to minus AYX. So the way you can think about this is at the beginning of time, give all of the edges some orientation, which you can pick in a random way. I mean, in any way you like is what I mean, not random, in any way you like. Pick an orientation for the edges. And then, because when I only want to make the assignment for each edge with the standard orientation, but then you understand that the opposite orientation of the edge is related to the one that you picked. So that's how we, so this edge I will draw like that, as perhaps that's the standard orientation, and then if I ever want to discuss the opposite area orientation, I do it with this minus sign in here. And say this is defines the edge in the opposite, the A on the opposite orientation. Now another thing I want to do, because you have to be a little bit careful with boundary conditions in order to make things work out, is to, if you imagine this as a plane, I want to compactify it. I want to add another point over here. You can think of it as the point of infinity, just an additional thing. And I'll join this point to every boundary point by an edge. So I won't draw them all, but every single boundary point is joined by an additional edge. I'm adding them in to this point of infinity. This is like a base point which will play an important role in some of the equations. And then the phi, which was defined at first only on the points in lambda, so this is the points in lambda. We extend by setting phi equal to some value. And at the moment, I don't want to tell you what that value is. I will just say it's fixed equal to some specific value at this point, and we will come to that later. So phi star is fixed to some complex number. Chosen later. Now, I want to describe the action for these two fields. So let's first.
Do you have some A's on those edges? On these edges?
Do I have some what?
Some
Yes,
A's.
I have some A's. I have some A's on these edges as well. Yes. Yes, indeed. So basically what I've done is I've made it into a sphere, right? A discrete sphere. Now, Higgs action. So you know that we're going to set up a probability measure on the space of this A's and Phi's, and this is going to involve this Higgs action and other actions as well, which I want to write down and then take the sum of them. So the Higgs action, S.
David, one
Yes.
question. Why do you call it a Yang-Mills field?
Because I didn't want to call it anything else
Okay.
for the time being.
Okay.
So Higgs, I had a problem with notation and collision. So the Higgs field, Higgs action is a function of both A and Phi, and it's given by 1/2 the sum over edges xy in E. E is the set of all edges, including these additional ones that I've added in, of phi x minus e to the I. Now there's an unfortunate problem here, which is that there are two e's. Actually, I'll put that e somewhere else, let me, so we don't have this problem. X, y, phi, y. So if you were to look up in the books, you would normally find the electric charge sitting there, also called E. But I prefer to put it somewhere else to keep my sum equation simpler. Pardon?
But lowercase e.
Lowercase e,
So there is
yes.
no problem. Lowercase is not.
And then I want to add to this a sum of x in lambda, right? Not summing over anything at the base point here. V phi sub x, and I will draw a nice little picture of what the V is supposed to look like, and then tell you what it is. So, firstly, it's not actually a function, it's actually invariant under rotations. Phi is a complex number, and I can multiply it by e to the I theta and turn it around. So I'll make it a function of the absolute value. And you want it to look like this. And the actual choice that I want to make is that V of phi of x is lambda phi x absolute value or complex modulus to the fourth minus 1/4 mu squared modulus of phi x squared. And then there's a constant. And the constant is so that I normalize it to 0 at its minimum there. And the minimum takes place at something like mu over square root of 8 lambda. That'll appear later in some of the ways.
This e is different from the other e.
And this e is just a constant, yes, to fix it like this, and it is different from
I mean,
the
from
other
the set of edges.
That is different from this e, yes.
And the edges are oriented, your sum over oriented edges there.
Yes.
Here,
That's why you have to
no. you sum over, you only sum over, so it all sums over edges are unoriented. Unoriented.
Probably you get the same if you.
So, in other words, there's one edge, which is an
It's the
edge with
same.
a standard orientation, and that's the one I'm summing over. I sum over edges with some orientation. With,
Look at the
okay,
same
I
if
agree.
But wouldn't be
Sorry,
the
it's
same.
confusing. I agree that we're summing over edges with orientation, but only with one of the two orientations.
No, you get the same twice.
get the same thing.
thing
You
twice.
get the same thing twice,
Okay,
but I
okay.
want to actually define E to be one, summing over one edge with its standard orientation. I mean, summing over an edge with its standard orientation. Otherwise, we'll get quite confused later. All right, so that's the Higgs action. And phi, yes, is called the Higgs field. Now, just put that on one side for a moment, and let's now look at the Yang-Mills action. So Prof is right. I mean, normally you would call this the electromagnetic field.
Yeah.
And A would be the vector potential of basically Maxwell's theory, but I want to call it Yang-Mills field instead. Yang-Mill action. So now what we're going to need is things called plaquettes. So these are the basic faces of this. So we have vertices, edges, plaquettes, and even higher dimensional cells. So this is a plaquette like this. Let's draw it. There's another kind of plaquette too, which is this kind, triangular ones. Now, if you give me a plaquette P, so this is in the set of faces, which I will call capital F. So there's just two different terminologies. I mean, people in, let's say, algebraic topology would call these, are thinking about simplicial complexes and things like that. They would call these things maybe faces. Physicists call them plaquettes. So I've used P for plaquette, that's a standard thing in all the physics literature. So plaquettes also come with two orientations. And the orientation tells you how to define the boundary. So there's two of them. And it's the same situation as with the edges. Sometimes we will be seeing the sum over plaquettes in the set of faces. And what that means is you sum a plaquette with a standard orientation that you have picked for plaquettes. And then we have things called two-forms, which obey a rule like this to tell you what happens if you want to talk about the plaquette with the opposite orientation. And so if you give me a plaquette, which is comes in two styles, maybe that's a plus and that's a minus, and we're given a gauge field A. And I've defined the derivative, the exterior derivative, dA, at the plaquette P to be the sum over edges xy in the boundary P of A xy. You may prefer to think of that as the curl. So for this plaquette, if I want to know what the exterior derivative of the gauge field on this plaquette is, what this says to do is to take the gauge field with this orientation, add the gauge field with that orientation, in other words, calculate the holonomy of the gauge field around this small plaquette, just like you have explained very nicely already. I'm just going over this again to remind people. And then we will find, if we follow this definition, that if we reverse the orientation, we will find that dA minus P is minus dA of P. And I'm going to be using this unusual D here because there are lots of integrals with respect to A's, like D, other, which are totally should not be confused with this discrete curl. I didn't define the action yet. Hang on. Squeeze it in here. So the Yang-Mills action, this is a two-form. So A is a one form, an assignment. You can think of the edges as being like vectors, right? Directions. You're assigning numbers to vectors. That's very like a one form in differential geometry. But then when you take the exterior derivative of it, you get a two form because it lives on plaquettes. It's an assignment of real numbers to plaquettes. And two form because, I call it a two form because it also obeys this alternating property. Now the Yang-Mills action, SYM of A, is 1/2 sum over plaquettes in the set of faces, dA sub P squared. So Thierry was explaining that the exterior derivative of A is also called the curvature in Yang-Mills. It's in electromagnetism, it's this matrix that contains both the electric field and the magnetic field all bundled together into a two form, which I think he explained also. So, the only thing I haven't quite got right yet is if I don't put this electric charge in here, then we can put it in there instead. It's equivalent by scaling dA. So much for the Yang-Mills action. Now let's take a look at the gauge invariance. So suppose I construct the following measure. I'll take the Yang-Mills action and the Higgs action, and then I will take the Lebesgue measure. So for every edge in the set E, there's a Lebesgue measure. And I'll take the Lebesgue measure for the field phi. That's the Lebesgue measure on the complex plane, so it's two-dimensional. I want to put that in my notation. Okay, now this is a measure, but it's not normalizable. Because there's a non-compact group of symmetries, the gauge invariances. So the symmetry is that you replace pi x by phi x times e to the I theta x. And at the same time, you replace axy by axy, and I'm never sure that I've got this sign right, yeah? D theta xy. Now this d theta xy is theta x minus theta y. That's definition. Right, so we're purposely using the same symbol, d, for two different things. So they just act on different spaces. There's a d that I've defined right here that acts on functions, that acts on one forms. And now right here I'm defining with the same letter a d that acts on the space of zero forms. Like this.
Why don't you use an exterior derivative notation?
Because I don't want to confuse the d because there's a d here.
Oh.
And we will get confused if we have two d's or some we might get
That's
confused.
agreed.
Why do you choose to set it up in the non-compact forms and rather than
Because you can't get to the continuum limit very easily without using the non-compact form. So, I mean, the continuum limit is expressed in terms of the Lie algebra. So, the Higgs mechanism is certainly much easier to explain in the case of the compact form, and I'll be doing that in a moment because I'm going to prove that this is actually equal to a compact form. Then we will have the best of both worlds by this procedure.
when people do simulations, they always use the compact.
They always use the compact form, that's right. Much nicer, no doubt about that. But if you want to, if for example we're able to construct four-dimensional field theories or three-dimensional field theories just in the mathematical sense, then we're going to have to understand the non-compact forms. At least I think we are. Okay, so yes, so as Prolog was saying, we've now got two d's, and one thing that plays a role, that I'll come to that later, is that d squared is 0. All right. Now, what kind of a theta are we allowing here? Theta is it's a real number, and there's one real number for every lattice size lambda, and theta at the base point is 0. This is a non-compact group of symmetries, and as such it means that there is a kind of Lebesgue measure, because this is invariant under this transformation, if I've got the sign right here, I was not quite sure. This is not normalizable. So we want to make it normalizable because we want to talk about probability measures and verify various axioms for them. So to make it normalizable, we'll introduce a gauge fix, as it's called. It's a way of removing this symmetry. So what we're going to do is say that the total action is the Higgs action plus the Yang-Mills action plus something called G, which is a function of A. I'll just write G here for the moment, where G, which is a function of the gauge field A. You could be more general than this, but generality gets in the way of being easy to understand, I think, sometimes. I want this property. If I integrate this e to the minus g of a, having made a gauge transformation, d theta, over all of the angles, real valued angles, except at the base point, which is fixed, remember. I want this to be 1, even though there's an a in here. I want it to be independent. So this is a special kind of function with the property that when you do this integral, you don't get any dependence on a. You'll want an example. Are there any such? So the very standard one to choose is g of a is 1 over, you can put an arbitrary parameter, sometimes called alpha squared, positive parameter, and then d star a, this notation here, elevate this, reverse these here. So this means it's an inner product. It's an inner product, and there is an inner product on the 0 forms, an inner product on the 1 forms, the 2 forms, and so on. These guys are going to actually be 0 forms. I haven't explained this yet, but I'm coming to what the d star is. So it would mean sum over vertices in lambda, sites in lambda, and whatever this d star a, and since it's an inner product, I would just say it's just the square. So it's like a little L2, it's a little L2 inner product. And by definition equals this thing. What is this d star a? So d star a, I'll first just give you the formula. It's going to turn out to be the divergence, so that will motivate this thing. You sum over y's, which are nearest neighbor to x, of a, probably divergence coming out, x, y, like that. So if I draw a picture, if you've got a point x in the lattice, then you have the edges coming out of it, which I want to orient this way. And I take the a, so this is the nearest neighbor y, I take a x y, like that. So it's the divergence, right? The discrete analog of the divergence. But the other important thing to know about it is that it's actually the adjoint. So the star means that it's the adjoint. Adjoint for the inner product. Now this inner product is for 0 forms, 1 forms, 2 forms. So what's happened here is that A was a 1 form, And when you take the divergence, or this d star of A, it becomes a zero form. It's kind of there. So the adjoint reverses the arrows. It goes in the opposite direction in terms of how it maps to the way that d goes. Right, now, so now we have, this is a bloody nuisance. Hung around here a lot, I would get used to this blackboard. Right,
And
so
here you take into account the
exercise.
the orientation, AXY in your definition of
Absolutely,
divergence.
yes, that's critical.
Takes the values.
Absolutely, that's why I drew the arrows out. That's the A, the way the A's have to be done. So you can think of it as a flow outwards from a point.
Now you complain about errors. Now you should complain about errors.
Which errors do you want to complain about?
No.
This, I claim this is an example here. So it means that you have to verify this equation. Okay, so check this equation holds for this. Alpha is greater. Well, actually, you'll find if you try to check it that you don't get 1. You get some constant. But the important thing is the constant won't depend on A. That's the crucial thing. So you can divide through. So maybe I should actually add here a constant.
Which depends on number.
So it's, if you choose that constant correctly, then you will get this. But you won't be able to do that without knowing that something like d star d is invertible. So that's actually why all of this nonsense about adding these extra edges and fixing the base point equal to 0 at the start. So that plays a role in that.
So there would be a problem in the non-abelian case.
Oh, well, definitely there'd be a problem in the non-abelian case because this would be the wrong thing. You'd need a covariant derivative then. And then there could still be a problem.
There's a thing called Gribov ambiguity.
Yes, there could still be a problem with Gribov ambiguity. So for this introductory lecture, I thought I would stay away. I mean, Yang-Mills normally means non-abelian. I just don't want to deal with non-abelian cases at this moment.
So it has a name, this gauge fixing? This particular
This one is called the Landau gauge,
Yes.
or maybe the Landau gauge. Now I always get confused about this. So sometimes people like to take the limit as alpha goes to 0, which forces the divergence of A to be 0.
I think it's the
Is that-
generalized Feynman line.
General-
Yes.
it's
Because
gen-
alpha equals 1 is Feynman.
Feynman.
And alpha goes to 0 is lambda. And it's sort of
Lambda.
interpolate.
Very good, thank you. Right. Okay, so that is, but I won't actually need this example, so I'm not going to do this exercise for you. Now, let me just mention, if I haven't got to the end of my time, without getting anywhere, I'm not doing so badly. I want to talk about which kinds of observables I'm going to allow.
Sorry, I mean, g of a is quadratic, no? So when I
yeah.
introduce in the integral, there will be still a quadratic part.
There will.
And you say it goes away somehow.
Well, so see what happens is, using the fact that this is the adjoint, you can write it as d star A, right?
Yeah?
And then you can
Okay.
evaluate.
Okay,
I
I
mean,
need to do the exercise.
yeah, you
I
have to
wanted
do the
to be sure
exercise,
that
right,
it's-
yeah. And if you can't do the exercise, it's probably because I've done what I usually do and forgotten to tell you something crucial, but I think it should be good. So just for observables, okay, we want, you know what gauge invariance means.
So just to be sure, okay,
Yeah.
it's not, the result is not the exponential minus g of a. It's
Yes.
not 1.
It's not one, no.
No, I mean, usually it's one, a non-exponential of minus g of a on the right hand side.
So I think it's not one until you chose that constant.
Maybe the following example is helpful. If you do the one-dimensional integral e to the minus x plus y all squared,
Yeah.
dy
Yeah,
doesn't
yeah,
depend on
yeah.
x.
Okay, yeah. This works.
Yeah, so what you have to do is to show that there's a theta which you can put in.
Yeah,
those
sure.
cancels
Okay,
together,
sorry. Yeah. What's confused?
Which is why I'm going on about whether you can invert dd star. Now, let me see. So observables. Okay, so I'm getting ready now to say I'm getting ready now to define the expectation with this extended action which has this gauge fix in it. And the point is that this is a rather arbitrary choice, this G. And we want to know that it doesn't actually depend on what choice we made there. So that's going to be true for functions of phi and a. These are the things we're going to observe, which are gauge invariant, which means that they should not change when you make this change of variables inside them, and which have to have an additional property, which is not so standard, periodic in A. And then, of course, just for technical reasons, it depends on finite number of fields only. So, for example, here's a nice observable, one of many. You could take phi x e to the I a x y phi y for an edge x y. Oh, with a conjugate, yeah. Which way around do I? No, I want the conjugate here, I think. Well, once again, when you try to check this is gauge invariant, it'll depend on whether I had the sign right here for this. Maybe anyway. Okay, so the idea here is that if you have a field at a site y, in Thierry's terms, it's an element of think of it as a fiber above the point y. Before you can decide how to multiply it or how to take a scalar product of some kind with another field in another fiber, you have to parallel transport it so that they're at the same place. And then you will not have trouble with violating this gauge invariance. Now, what about this periodic in A business? See, there's an e to the IA in this. Well, there isn't actually an e to the IA yet. So maybe I shouldn't have. Maybe I'll explain this in a moment when we get to the proof. But anyway, this is a condition. Sometimes most people would say that observables are just simply gauge invariant functions without this condition. Maybe they'd like this finite number of fields. But in the papers that I referenced up above, these are called integral charge observables. And I don't want to explain why at the moment. The ones that are periodic. Okay, so what's the theorem? Or what's one of them? I mean, there are many theorems here, but we can do one of them here. So we want 2 dimensions or more. Fix u and u times e over square root of 8 lambda. What I mean by fixing it is we decide right now that they will take some arbitrary positive values, and then I want to consider what happens as we allow lambda to go small. So for lambda sufficiently small, so this lambda hasn't been seen for a while, but it might be up there somewhere. There's the lambda in the Higgs field. There's the mu that was also being mentioned. So the only way that you can have this and this fixed is if when you're taking lambda smaller, you have to take e small too to compensate. So this is you could discuss actually the real limit as you do this, which would give us kind of a Gaussian field, as you will see in a moment. But the statement of the theorem is that even near that limit, something good happens. You don't have to take it to the limit. For observables F and G, firstly, there's a limit. Then the infinite volume limit, as we take lambda up to ZB of F. So I haven't defined this symbol, but this is the expectation. Just squeeze, this is not good, but I'll just squeeze it in right here, or I'll write it at the bottom. So this is the expectation which is associated with this action, which is the sum of the three terms. Do I have it still? Hopefully, somewhere. I'll write it in again in a moment.
Yeah, no, it's there, on the left.
On the left. Left.
Top of the bottom board.
Bottom board, yes, okay. I'll take your word for it, I can't see it.
Well, no one can see it, but if you move the board down a
maybe
bit,
it's under the board. Okay. There we go, yes. So instead of doing this measure, we're doing this measure with the gauge fixer in. And this is the expectation, which depends obviously on the volume. We take the infinite volume limit, that defines an infinite volume expectation. And then, that's not very exciting, but actual Higgs mechanism comes next. And if you look at F, G with a subscript X minus F expectation, G with a subscript X expectation, take the absolute value. This will decay as a constant e to the minus W and M, and that's a norm of X. So this means translate the observable by X. It depends on finitely many fields, right? This one, this one, and this one. Pick them all up and move them over by X. So there exists M, which is actually approximately equal to this other combination right here. I'll call that M sub A for the mass of the gauge field. I don't want to be precise about that, but as you take this lambda and e to 0, that will become more and more correct.
What happens, David, when the gauge field does not have a mass?
What happens if the gauge field doesn't have a mass? Well, the assertion of this theorem is that it does have a mass. If you take lambda smaller. So you're asking if there's a phase transition, right?
Yes.
Okay, that's why I gave this reference right here, Kennedy King, which discusses order parameter, what order parameter is not 0 versus what is 0 when you go across this phase transition and things like that. It's a nice paper. So yes, there's a massive phase, and not by this theorem, but another theorem in the Kennedy-King paper, there's a massless phase as well.
Is there a confining effect?
They don't discuss that, and I have to think about that to answer it, so I can't answer it right now. I mean, one thing, well, I can say something about that when we get a little further along in this. And I'll show you what this is equivalent to as a compact theory. Okay, so this exponential decay, this m, okay, we're all in the Euclidean world here, but we've discussed how these things have continuations in the real world. In that case, this has the meaning of the mass of the photon, or the gauge field A. And so the big deal about this theorem is that when people first proposed gauge theories, there was a general opinion that they could only describe massless particles. And which was fine in the case of electromagnetism because the photon is massless. But as a generalization, so we now believe that all forces are gauge forces, basically. Gravity, electromagnetism, weak force, weak electromagnetism, strong force. But at first they were thought to be predicting way too many massless particles, which are not seen. So this mechanism shows that having a massive gauge field is not incompatible with gauge theory and relativity.
I think in the continuum, this was so long ago, but so. Yes, massive electrodynamics.
Yeah.
Why, it makes sense.
Even
And then
Schwinger-
your gauge fixing condition, d mu a mu, right, is equal to 0, or 1 over 2 alpha, which you're putting it. Observables are everything that commutes with this.
So I don't know what the order is, but in the Nobel lecture, Higgs mentioned Schwinger, or massive gauge, this possibility. And also, actually, Philip Anderson in condensed matter proposed this mechanism, but nobody in elementary particle physics was much talking to the condensed matter people at the time. Okay, so it's a nice story anyway. Now, we still haven't seen why there should be a mass, what produces it, what is the actual mechanism. This is just a theorem that it works. So let's look at the following equivalence. So I want to explain this equivalence. The nice thing about gauge theory, when I was working in it all these years ago, was these equivalences. This is the part I actually like the most about the whole subject. Lots and lots of models, either by duality or by little pieces of algebra, like the one I'm about to show you, are equivalent to other models, and sometimes they're quite startling, actually. You won't find this one so startling, but another example of exactly what I'm about to explain, which I like very much, is that if you take the same model that I'm talking about here without the gauge field, this thing here focuses the field on a sphere of this radius. Well, it's a it's a circle with this radius because it's in the complex plane. So if you take what we've called the rotator model, where the phi just takes its values in the circle, and you make one small modification in the model, which is called going to the Villain approximation. It's a nice thing to do. Then this model is exactly equivalent to a Coulomb gas in 2 dimensions, which is fantastic and very surprising until you start reading these papers and seeing what the general picture is behind. And it's the same equivalence that I'm talking about here, but this one goes like this. I'm going to set E equal to 1 because otherwise these equations get too much. I'll sort of set it equal to 1, write this equivalence down, and then pop the E back in later when we need it. So we're starting with an integral over gauge fields, so that's the space of gauge fields is R to the E, times, and an integral over Higgs fields, that's C to the lambda, complexes to the lambda. We've got this E to the minus S, a phi, and I remind you that this contains G, contains the gauge fix. And then we'll put in an observable. And I might get a bit lazy, but we have to do this with a integral over A and phi. I might leave these out because you can see what they are from here. Okay, so the claim is, this is a theorem, that this equals minus the integral over the interval from minus pi to pi to the power of E. So this non-compact space has been replaced by a compact interval here. You should think of this as U1. It's the end
to
of
the circle.
one. It's the circle, yeah. C lambda is unaffected by this whole thing. Then we have the sum over, I have to explain this below. I will call them vortices, V. Such that exterior derivative of V is 0. E to the minus 1/2 sum over plackets in faces, exterior derivative of A at the placket P plus the vortex at the placket P squared. I'll put this all in parentheses because basically the price you're paying for replacing this non-compact integration by this compact integration is to replace e to the minus just the Yang-Mills part of this by this new Yang-Mills function of A. And if the equation goes on, we have the Higgs part, which has not changed. S Higgs, still the same function of A phi as it was before, and we have the observable A phi.
And G.
No G.
No G.
No G, right? There's the G, but this side has no G in it. Which is very useful, right? Because it proves that the expectation of one of these gauge invariant periodic observables is independent of the choice of G. That's one little consequence of this. Although there are other ways to prove that without doing this. Now, what is this vortex business? Where? So V is an assignment of integers to plaquettes, the function on phases. And so we have to sum over all of those things here. And but they're limited by this restriction that the exterior derivative of V is 0. So I want to explain what that means now. So let's see, let's look at a picture in D equals 3. So look at a box, a cube. So these are plaquettes in 3 dimensions, and this is like the fundamental, just like we added in fundamental faces, I'm adding in fundamental 3 cells now. Some of them aren't this shape, right? Because one of the boxes would look like this. You join, can I make a box out of this? Yeah.
But you are in 3 dimensions, so you take a square and the
No.
you take a pyramid.
So there's a funny shaped box.
Just
No,
a pyramid.
Yeah, this is like a suspension, but I guess there are no, I don't think there are any of these.
You take a square and you add this infinite point to the square.
Yeah, but I only join this to the boundary. So I don't think there are any strange cells like this at the moment. Okay, so why am I drawing this box?
Yeah,
So-
but you are in 3 dimensions and there are
No, I mean, I am in, okay, 3 dimensions, yes, there are, yes. thank
You have the
Right,
square
right,
and you
right,
take the
right. Yes, so there are some other shapes, things as well as this. But anyway, given one of these 3 cells, you make an assignment. So dV, given V, in this space, dV is an assignment to a cell. Given a 3 cell C, and given V, dV is the sum that I'm going to draw in this picture and then write down. So what we have, a V is an assignment to these plaquettes. So I would orient them so that it's looking like this. These are the, I draw the assignment like this. So I have a V, there's one for every face. You can think of it as the flux of V coming through the face. And I sum over plaquettes with the right orientation in the boundary of the cell C of V sub P. What it means, if you think of this like Faraday did as lines of flux or something, it means that there's nothing being created in any cell.
So in 3 dimensions, this will be a divergence on the dual lattice.
It could be a divergent sum. No,
It's
So
an
divergence
exact,
take a dual lattice. So in 3 dimensions, if you have these buckets, they
that's right.
correspond, they correspond to what to call vector fields, whatever.
it's an
on the
exact
dual-
form.
Exactly.
You could,
It's
but
an exact form.
I think maybe what you're getting at is this. If you looked at the support, if you looked at the plaquettes, which were the support of a piece of P, which obeyed the condition, so dV, this is condition here, what does it mean? dV equals 0 for every plaquette means that in the dual lattice, you have closed circuits, and these plaquettes, which are threaded by the circuit in the dual lattice, are the support of a V. And so the way to get a dV, the way to get a flux assignment which obeys this exterior derivative condition is to choose plaquettes which are threaded by a closed loop, and then you will get dV for that particular assignment equal to 0. And of course you can take any number of any linear combination of closed loops. So it's a conservation law. Now it's much easier to understand in 2 dimensions. In 2 dimensions there are no 3 cells, and dV equals 0 simply means that there must be, so d equals 2. The sum of V sub p over all plaquettes has to be 0. So in this case, plaquettes there's an assignment of V to every plaquette, and some of them can be like positive assignments and negative assignments, and the sum of them over all plaquettes has to be 0. Like charges.
But you have to choose an orientation of the buckets, no?
You have to choose an orientation, that's right. So, I mean, basically what we're doing is like taking it's like in 3 dimensions you'd have infinitely long ones like this, and you are constant in this 3rd direction. It's another way of taking a 3rd dimension out, but it just means that the number of flux assignments coming out is equal to the number of flux assignments going in that respect. So that's the theorem. Yes.
I'm confused with the D. Is this the co-boundary or a boundary? It's a co-boundary.
V is a. You're confused with the V's, did you say?
The D's.
The Z's.
The D.
D, yeah. This D is the, so D always,
Does it increase the degree?
it increases the, it's like the exterior derivative in differential geometry. It takes you from 1 forms to 2 forms to 3 forms and so on.
But then, how is it that in 2 dimensions it is not just 0?
The D is 0.
It's a finite domain.
But let me say it this way, okay? In 2 dimensions, if you draw 2 dimensions, right? I've joined it to a point like that, right? Now, there is a condition, there is a compatibility condition to solve the previous D, which is that the flux out of this thing has to be 0. So the way to deal with that is to fill this in with a 3 cube, right? And then what you're doing is you're dealing with exact sequences on disks, and so then everything works. Okay, so that's a somewhat technical answer. I do want to show you that an exact sequence plays an important role, and I think I've got some time to do that here. So in other words, why this theorem is true. Well, 2 things I have to do. One is I have to show you why this theorem, it will motivate. I'll use this theorem to motivate this Higgs mechanism that we have here, but don't let me know about that theorem yet. So let's do that first. Oh, I want to make one other remark. It's a very surprising thing. This is truly gauge invariant, compact gauge invariant. It's a claim, all right? I have to explain it a bit. So a very odd thing has happened here. You broke the gauge invariance by putting in this gauge fix here. You do this transformation that I hope to explain, and you end up with a compact gauge invariance theory. Compact means that you can do a rotation. Let's see what I can rub out here. Down to here. So let me explain it this way. This whole thing inside the parentheses is 2 pi periodic in each AXY. Now the AXYs are being integrated over this thing. And so periodic is rather important because that allows us to interpret this really as a group. Why is it periodic? Well, first, before we do the periodic, maybe I'll just point out why this is a good thing. So, when you look at this transformation, AXY goes to AXY plus d theta, xy. Because you're integrating the theta over this, and the A rather, over this space, and also I'll be wanting the theta to be in the same interval, what do I want this kind of addition to really mean? I want it to be a mod 2 pi addition. And for that, I need this claim up here that everything is periodic in each A. Then it will be a mod 2 pi addition, or I can make it a mod 2 pi addition. And then in that case, I stay on the same space that I'm integrating over when I do this transformation. That's the important point.
Somehow you have this, but you have infinitely many of these periodic guys, so this is cancelled by normalizations.
No, I'm just making a claim right now that I can make a gauge transformation, same formulas that I had before. And normally that gauge transformation, if you add this to AXY, will take you outside this space. But this thing is periodic, so I can do a mod 2 pi addition instead of just an ordinary addition. And it's in that sense that I have gauge invariance. This is the gauge invariance I have for this thing in parentheses. The rest of the argument, the Higgs part, plays no role in this. It just goes along for the ride without any issue. Now, let me just point out why it's periodic. So suppose I change one edge by adding 2 pi to it. That's something I can compensate by absorbing it into the V sub p. I'd like to, I am in danger of not finishing, so I'd like to just say that and just leave it for discussion afterwards. All right, so let's now see the Higgs mechanism, if we can, using this remark. I mean, Roman, you are right in that it became gauge invariant by putting together lots of different intervals like that, but that comes up in the proof. Let me try to explain where this mass comes from. So this is the Higgs mechanism. So we just make the change of variables. Change variables. we write 5 sub x is equal to rho sub x e to the I theta sub x. In other words, we write this in polar coordinates with a theta that's between minus pi and pi. And this rho is now a positive real number. That's, and we want to make that normalization. At the same time as making this change of variables, we change AXY to AXY plus d theta. And because d squared theta is 0, when we look at this, we won't see it. So after we made this change of variables, the right-hand side of my theorem of the equivalence. So this thing here is the integral of minus pi. Now I'm going to put this e back in. So instead of minus pi to pi, it's pi over e. To the e. Cross r plus to the lambda sum d, which vortices which are conserved, e to the minus 1/2 EAP plus v sub p squared. And the interesting thing is now finally the Yang-Mills, the Higgs part is going to do something good for us. So I've just been letting it ride along for the moment, but let's write out what it is a bit more explicitly now. It's e to the minus 1/2 sum rho x minus e to the minus I e a x y rho y absolute value squared. And then we have this Lebesgue measure, which isn't quite Lebesgue measure, because remember, this Higgs action had 2 terms in it, and one of them was the term which is illustrated by that diagram up there, that graph. There's an e to the minus v of rho x d rho x, as well as the integral over the gauge field, which I have to squeeze in here. Like that.
Isn't this E already incorporated by the fact that you integrate over P over E?
Well, what I've done is scale the gauge field back by putting it here. Oh yes, you're quite right. Which one do I do? No, this is correct. So if I want, I mean, this is a lie. The right-hand side was at e equals 1, right? But I'm just putting the e back in. Okay, so if I had had the e in the right-hand side, or do I mean the left-hand side? I mean the left-hand side of the equivalence. I want the compact side of the equivalence. No, it's right-hand side. So I think I've got it right. If you put the e in here, then the periodicity is over this much larger interval if e is small. Now, let us take, notice there's no, I mean, there used to be a phi x and a phi y here, but we wrote phi is equal to rho times this, and this disappeared because we did the gauge transformation. It got eaten. So the thetas got eaten, is the phrase, the technical phrase used in physics, eaten by a gauge transformation. That's a good thing already because it was those thetas which correspond to tangential movement inside the Mexican hat potential, which are massless, and they are being made to disappear by this thing. So what will happen if we do this business of taking lambda small, keeping this thing fixed? What we're doing is we're holding the minimum in one place, the mu, and we are concentrating the measure, the phi, we're concentrating rho onto a particular value. So this whole thing here is going to be approximately equal to, I'll just write the whole thing, minus 1/2 sum over x in that, xy in edges of rho x will be almost equal, this minimum here concentrates the rho, concentrates the measure onto rho equal to that value. So we will have mu over square root 8 lambda, and we'll have two of them because it's a square. And we will have 1 minus this thing, right? I'm factoring out, I'm saying the rows are constant, that's an approximation. Factoring them out, 1 minus this exponential here, right? When you take the absolute value squared of 1 minus this complex exponential, you'll get a cosine. So there will be something like, well, I'll write it here first, just to make it 2 steps. 1 minus e to the I e a xy squared. This is approximately equal to minus 1/2 sum over xy in e u squared over 8 lambda. And this guy, if I do a Taylor expansion, the ones will cancel and you will get something like e squared here, a xy squared, and a 1/2. I think the 1/2 gets cancelled because there are two of these. This is what we defined as the mass in the theorem. The classical mass, you should call it, because it's not the real mass. The real mass is this m that appears in the theorem, the best possible m. But this is the classical mass, this thing here, squared. And so it's the appearance of this quadratic term. And notice this is a good approximation by the quadratic part for this whole thing here, because the rho is stuck on the real line, and you would have Gaussian fluctuations if you wanted to do more than what I'm doing here, and actually that you have to prove the theorem, you have to use what's called a cluster expansion to make this all work. But you can see that in this limit, it's very much like a parabola. That's how you will actually get a Gaussian theory in the limit. And the A is also Gaussian, but massive Gaussian, because this factor here gives you an a squared, and you can combine that a squared with, for a moment I'm ignoring this thing, with the square of this thing. And that gives you a massive Gaussian propagator or covariance for the gauge field. This is the Higgs mechanism. Now you may be very worried about this thing here, but the fact is that when you take this limit, the action of these V's is enormous, exponentially large. So there's a long argument, it's a long tedious paper actually that I've referenced for this theorem, but it's a cluster expansion that says that vortices are extremely rare events, and that the outcome is as if they're not there. So that's how everybody, the phi got a mass because it's fluctuating inside, it's lost its angular degrees of freedom and it's fluctuating inside that parabola there, and the A got a mass the way I explained. Everybody is a man who got a mass in this way of writing the theory.
So if we ignore the vortices for now and the Higgs field and just pretend we had this mass, it's still it's a free field, but it's somehow one level up, right? The A is on the edges, and then the gradient A is on the plaquettes. But I guess you can still solve it in the same ways. That's what you're saying.
Well, I'm
So we're
saying
just
that's
looking at the Gaussian case.
yeah, that's the underlying approximation, and the cluster expansion is an expansion around that Gaussian, in corrections to that Gaussian. I don't know that you'll find out how to do that actually, that cluster expansion, by looking at Erhard Seiber's paper, but it's a long story and we can't do it now, unfortunately.
So this star, we somehow do not know why you introduced it at all.
The star, no, you do, yes, you do when I try to prove this theorem in the remaining 2 minutes. Okay, which I'm going to do now. So I'm going to try and prove this. It's not very difficult in some respects. So let's keep the theorem here. And let me say a few words about the proof. And then you will see what all that is about. Proof of equivalence. Well, you know, there may be a constant here, but that cancels out when you look at the expectation. I'm going to just omit the observable, make it short and frame. You can let it just rides through. The hypotheses are such that likely yet it has the same properties as the Higgs does, and so it rides through. So we're starting with R to the E not C to the lambda. And then there's the Yang-Mills action, and there's the Higgs action. And then there's the gauge fix, which has to be given special love and attention in this argument. Okay, now what's the first? That's what we actually have on the right-hand side if I leave this thing out. Now, the first thing I want to say is that I can, this is gauge invariant, this is gauge invariant, non-compact gauge invariant. So I want to integrate, I want to average this, replace this by the average over compact gauge transformations. So they look like this. 2 pi to the minus lambda, 1 factor of 2 pi for every side, in other words. Integral minus pi to pi, this is the compact part of the gauge invariance. Lambda. D lambda theta. I can just put this, and this in because the rest of the argument is gauge invariant, and the rest of the integral.
Wait a second, so initially you only had a G of A without a theta.
I know, but I put, that's right. Oh, I'm sorry. Initially I only had that, and I didn't have this and this. What I'm doing is I'm averaging the G, or the e to the minus G, over compact gauge transformations. But it still depends on A. I mean, you know, we had a condition on G that it integrates up to 1, but that's under non-compact gauge transformations. So it depends on A in some strange and complicated way. Now the next step is to replace this R by a compact interval, which goes from minus pi to pi to the e, and compensate by summing over what that compact interval could be. Now, that's a sum over something called a, which is in 2 pi z, so it's integer value. It's a label for the possible intervals. And I should, of course, have something like a little a plus this, but I choose to put this little a somewhere else. I put it here. S, Y, M, Yang mills, capital A plus little a. E to the minus S Higgs. A, comma, phi. And we put a little a here. And then we have the rest of we have this thing. And that also should have a little a in it. So I'm going to put that in there. Every a is getting replaced by a plus little a. Now here, you can cross it out.
Also just observable.
The observable I left out, but
Yeah.
I'm leaving it out for the same reason that I'm about to explain here. It does nothing. I've crossed out the little a that I'm supposed to have here. Why? Because it's periodic in capital A. And I'm just moving it by 2 pi times an integer. I certainly don't want to cross it out here, because we're coming to Roland's question. And I cross it out inside the observable too. Next, write this sum over A as a sum over vortices, such that dV is 0. And then sum over A such that dA is V. This is a rewriting of this sum. Everything else is the same. Now, it's a rewriting, it's kind of a pigeonhole principle. You're grouping the A's into equivalence classes. There are all those A's whose exterior derivative is V, then there's the sum over all the possible V's. But all the possible V's has to be restricted by dV equals 0, because this equation forces that, and it's an exact sequence actually. So this is where adding in all these extra cells and so on is playing an important role now. I'm going to be using the fact that I have an exact sequence. I'll write it down in a moment. But anyway, that's a rewriting of this sum. Now, we can rewrite this even some more. dA equals V is equivalent. I'm going to tell you what all the solutions of dA equals V are. It's A has to be of the form A sub V plus V of, I think I called it V for some strange reason, because I couldn't think of another letter. What am I saying here? It's like in ordinary differential equations, which are linear. Every solution is a particular solution plus a homogeneous solution, right? I can solve dA equals V, and this is again using exactness, by finding one solution, which I will just choose and call A sub V, and then adding an arbitrary boundary to it. So in other words, the sum over A's that obey this equation is the same as summing over B here. Now I can rewrite what comes here. So I have e to the minus Yang-Mills. Now this Yang-Mills, I should write it out more explicitly because it simplifies, it has a nice form. It's really just dA plus the vortex at P squared. this part, the Yang-Mills only cares because it's because you replace capital A by A plus little a under the D. It only cares not what the vortex. It doesn't care what the A is. It only cares what the curl of the A is. You get that? So you can begin to see where this is coming from, right? This and this is going to end up being this. Now what about the rest of it? The Higgs, that just doesn't do anything much, because the A was crossed out. And then this part, we should carefully write this part out. 2 pi to the minus lambda e to the minus g a plus little a sub v plus b of theta plus b. Now comes the crucial point, so it's good if you can catch up with me here. Give you a chance to catch up, or I say the crucial point. So what I have done is I have substituted A is A sub V plus dV in this gauge part. So there's the A plus A sub V, and there's the dV, and there was already a theta. Now you can see what will happen when I try to sum over B. So I'll do the sum over B, so I'm kind of putting this part in instead now. I'm summing over B, and this integral was only over the compact thing, right? But the theta has been translated by an arbitrary 2 pi multiple. So the effect of this sum over B is to string together all of these intervals into one infinite interval. We have 2 pi to the minus lambda, and we have e to the minus g a plus a sub b plus d just theta, but theta is in r, so r to the lambda. Now this is what the condition on G was, exactly that this interval is 1, irrespective of the A field. So the gauge condition goes away, and what you're left with is what I've written on this side.
Can you repeat this point where the B disappeared?
Where this became this instead of, this was an integral at the moment from minus pi to pi
Okay, yeah.
to the lambda,
Yeah,
right?
you're right, okay.
And it became, yeah. So that's, I'll quit with that. Quit while I'm ahead.
So the same, so if you had not a abelian gauge field,
Unfortunately not, no.
yeah,
I mean,
well,
all,
none of this works, of course, but, right?
Yeah.
So then the result isn't known, is that right? Or,
well,
it should be
so for the compact formulations, the argument that I gave to get the Higgs mechanism works beautifully, said. But you don't know how to transform a non-compact into a compact in that case.
can you say that again?
So the argument I gave for the Higgs mechanism, which in the you see, I said
Yeah,
once we've got to the compact,
Yes.
I can use gauge invariance.
But you don't know what the compact is, and
If you don't know what the compact is, well, you do know what the compact is for non-abelian gauge theory because that's the Wilson action, for example. I mean,
right, but
because
you don't know what the vortices are.
you don't, well, I would say it this way, we don't know how to get from a non-compact to a compact version. That's just what we don't
But
know.
the dual for non-compact would be representations of this group. somehow.
Exactly, yeah,
Yeah,
yeah.
so you will have to integrate overall representation.
You would have, I mean, but it's not, the problem is it's not abelian, it's not, I mean, cohomology is an abelian construction, and C squared equals 0 and all of that stuff. There's something really big missing in that. It's a very interesting problem, how to do duality or I think first one should worry how to do duality for non-abelian gauge, which I haven't talked about here, but it's kind of a simpler question than how to do this transformation.
So in the compact version, normally be in a confining phase, that's when you've got a strong coupling.
Yes.
Which you don't normally see in the non-compact version.
Right.
I mean, how does this kind of reconcile?
I mean, in 3 dimensions, we know that the pure abelian gauge theory is always confining. I mean, on a lattice, if you put abelian U1 gauge theory on a lattice, doesn't matter what the coupling constants are, it's confining. It's a theorem of Goethe and Mark. So, I'm not sure whether that answers your question, but
Well, you're restricting to 3 dimensions in this context.
well, it's also true in 2 dimensions, but it's an easier theorem. Let's see, actually, wait a moment, it's 2 dimensions, I might be wrong. Let me only stay with 3 for a moment. For 3 dimensions, it's always confining. That's a fairly remarkable result by Goethe and Mark. And you know, there have been bogus proofs of confinement in 4 dimensions for non-abelian.
Yeah, I mean, I know there are kind of people thought they proved this.
But this is no one has found it. Now, maybe not so many people have read that paper because it's long, but of the few people who have, none of them have objected. It seems to be a correct paper. I can't remember the year, but something like 1986.
Is this in a situation where you couple to a scalar field with a mass?
No, it's pure non-abelian, pure abelian. It's all pure abelian gauge theory. So it's
Pure abelian is quadratic, and therefore presumably.
no, because it's the U1 theory. I mean, in other words, you put.
Are you talking about the compact?
Yeah, the compact formulation.
Because the non-compact one.
The non-compact is easy, right? But then it's not confining, probably, right? Yeah.
So there's dichotomy in the pure U1 case between the compact.
I think there is, yes.
So I still somehow do not see where the star appeared here, somehow, where it was, so it's somehow.
The star, well, you see, I have been using all the way through here, and especially in this statement, the exactness of the sequence. So what is the sequence? I'll just write the sequence down. Zero goes into 2 pi z to the, I'll add in the star here. It's a bit perverse, I'll factor it out. Because you remember that we always fixed the 0 forms to have a special value at star. So that's what I'm doing here. And then this is d into 2 pi z for all the edges, including the ones that go to the star. And there's another d which goes to the faces. We've been using this d and this d in this argument, and we've been using exactness at this point here. And exactness what I did with adding in the base point and so on, that's not what you'll find in the original papers, but to my mind, it's the easiest way, clearest way of expressing how to deal with boundary conditions so that you keep exactness. Then I have actually mentioned this one because in 2 dimensions we saw that it's a good idea to fill in the cone with a single cell, and then you will go to 0 if you're in D equals 2. And if you're in D equals 3, then you will go to, I got this right, maybe I should say it this way. Well, okay, that's where I would end in D equals 2. In D equals 3, I would go 1 more. Because I would fill in the interior of the 3-dimensional cone. So we're not using the exactness of the entire thing, although that is actually given to us by, if you fill it in, you've made it homeomorphic to a ball, if you see what I mean, and it's contractible. But we are using the exactness right at this level here. What I did. I like this argument, by the way.
Go to 0 in D equal 2, in D equal 3. From C.
In D equals 3, I mean, there are different ways of saying this because you can truncate these series in different ways, but I would do it this way. In 3, I would add in, so I've added in a lot of cells here. This is 3 cells. I've added in a lot of 3. In D equals 3, as I had trouble visualizing it till Roman was getting it straight, but if that's a 3-dimensional thing, right, and I join up the edges to the boundary, then I have to add in a lot of cells to make this work. And then I would add 1 more in, which would be a 4 cell. So there's just one for a single 4 cell, which is the interior of the 3 cone. And then I will go to 0 after that. There'll be a D here. But we wouldn't be using the exactness of that part, but we would have it if we wanted to. There's something interesting about this, actually. It's replacing the sum over integral over fields by integrals over exact sequences. And this same idea is in this BRST view or better still, battalion billing. What is it? Anyway, there is a really nice way of doing perturbation theory because it's the same for all possible gauge invariant theories, where you add in lots of anti-commuting numbers, and these are basically, it's not the same. This is integer cohomology that appeared here, but there's still the same idea that the integral over a rather nonlinear space, rather than integrating over the space that you might want to integrate over, would be all possible connections factored out by gauge transformations. Rather than integrating over a very nonlinear space, they were represented by projective resolution, so by exact sequence, and integrate over exact sequences instead. That's what all of those anti-commuting guys are. I only have a very vague understanding of that, but I think it's an interesting idea. So there's a general idea here that sometimes it's better to integrate over things represented by projective, by exact sequences than the original fields, because it's linear. Okay, thank you.